Okay, today I want to talk about the Laplace transform. The Laplace transform is a recursive function, and you'll see why in just a second. The Laplace transform goes something like this. We have the Laplace transform of some function, usually in terms of t or time, but it could be any variable given. It's equal to the integral from 0 to infinity of e to the negative st times that function of t dt. So one way you could solve this is by separation of variables, and I'm going to do that by assigning the variable u as being equal to f of t. Therefore, the derivative of u is equal to f prime of t times dt. The other variable I'm going to define is going to be e to the negative st, meaning that v is going to be e to the negative st over negative s. And then to solve, we take u times v, so that's just f of t times e to the negative st over negative s, so I'm going to write it like this, negative se to the st, and that's from 0 to infinity, and then minus this times this, but this is already negative, so I'm going to add, and then I'm going to factor out the s, which is just a constant in this case, and it's going to be e to the negative st times the derivative of t times dt. So it's recursive because to solve for the function you have to solve for the derivative of the function, and sometimes it's written as L of s. But expanding this first section out, you have it being equal to f of infinity over negative s e to the s times infinity, which is just infinity, and then you're subtracting f0 over negative s e to the anything times 0 is just 1, e to the 0, which is equal to 1. And then what you have here is something, the denominator going faster, growing larger, faster than the function grows. So therefore you end up with 0 at infinity. So all you're left with is f0 over s plus 1 over s, and all this right here is just another way of writing the Laplace transform of f prime of t. So for an example, let's say that our f of t is equal to 1. We just plot that, we just fill that in right here. That just means L of 1 is equal to f0 over s. Well, f0 of a constant is just that constant, so we put that over s, and then we add 1 over s times the derivative. Well, the derivative of a constant is always 0, so the answer is 1 over s. Now if we wanted to take the Laplace of a different constant, say 2, that is just equal to 2 times the Laplace of 1. And we can factor out the 2 because it's a linear operator. It follows the same rules that you can the same rules as taking derivatives or integrating. You can always factor out a constant. So that just leaves 2 times the Laplace of 1, which is 2 over s. So any constant is just that constant over s. Let's do another example. Let's say we're taking the Laplace of, I'll keep the variable of t. We just fill that in to our formula up here. It's just f of 0 over s. Well, replacing 0 with t is just 0, so you have 0 over s if you want, plus 1 over s times the Laplace of the derivative. The derivative of t is just 1. So what you end up with is 1 over s times the Laplace of 1, which we found out is 1 over s. So it's 1 over s squared. I'll do one more example. The Laplace of t squared is equal to f0 over s, which is still 0 squared over s if you want, plus 1 over s times the Laplace of the derivative of t squared. Well, that's 2t. I'm going to factor out the 2, and I'll just leave the t. And then we have 2 over s times the Laplace transform of t, which we found out is 1 over s squared. So that turns out to be 2 over s to the third. And there's a pattern that you'll see start to emerge. It goes like this: 1 over t, the Laplace of t to the n is going to equal n factorial over s to the n plus 1. And if you keep practicing, if you keep increasing the exponent, you'll find this to be the case.